All right, so today we're taking a deep dive into AI and how to make it more efficient.
That's right.
We're talking about those massive AI models, the
Hmm.
ones with billions of parameters,
Yeah.
those things.
Yeah.
And those are resource hogs,
They really are. Super resource intense.
really are.
Yeah.
So researchers are trying to figure out, okay, how can we make these things a little less resource hungry? And that's where this thing called the reformer comes in,
Right?
right? I mean, that's
Yeah.
what I've been reading. Like, it's supposed to be kind of a game changer in terms of efficiency.
Yeah, it's really trying to solve those core issues that make these models so demanding in the first place. But to really understand how the reformer works, it's helpful to kind of like understand why those large transformer models are so demanding. Like, where does that come from?
Okay. Yeah, break it down for us. What are the things that make these models such resource hogs? Like, what are the main culprits?
Okay. Well, there's a couple things. First, you've got the sheer size of these models, right? I mean, they can have billions, sometimes even trillions of parameters. So, think of those as like tiny little knobs and dials that the model adjusts during training to learn from data.
Oh, wow. Okay.
And then the data sets themselves are huge. I mean, we're talking gigabytes or even terabytes of storage sometimes.
Yeah, I was going to say, it's like trying to fit the entire Library of Congress on like a tiny little flash drive.
Yeah.
So
Right.
I can see already where the resource problem comes in, just
Yeah.
the sheer size of everything.
Exactly. And then you have the training process itself, which relies on this technique called backpropagation. And essentially, backpropagation is calculating the error the model makes and then adjusting all of those billions of parameters to reduce that error.
Okay. So that makes sense.
Okay.
But for people who might not know what backpropagation is, could you like really quickly explain it?
Sure, imagine you're learning to throw a dart, right? And each time you throw it, you see how far you are from the bullseye. And then you adjust your throw based on that error. So that's basically backpropagation. The model makes a prediction, sees how wrong it is, and then adjusts those parameters to try and get closer to a correct prediction.
Got it. So how does backpropagation, though, play into the resource consumption problem?
Well, to do backpropagation efficiently, the model needs to store something called activations. And activations are essentially intermediate values that are calculated at each layer of the model. So kind of like the footprints that the model leaves as it, goes through the data.
Okay, so it's not just the model, it's all the calculations it has to do and store along the way.
Exactly.
Got it.
And the more layers a model has, the more activations need to be stored, which
Yeah.
takes up a lot of memory. It's like remembering every single step you took from point A to point B.
Right, right. And I'm guessing these large transformer models have a lot of layers.
Oh, yeah, they do.
They do.
And to make matters worse, those intermediate feed-forward layers within the model are often much larger than the attention layers, which means they just gobble up tons of memory.
Okay, it's starting to sound like a logistical nightmare.
And then you have the attention mechanism itself, which is like a really crucial part of a transformer. And it allows the model to focus on the most relevant parts of the input sequence.
Okay, so like how we focus on certain words in a sentence to understand it.
Exactly, exactly.
Got it. But I'm guessing that this also plays into the resource problem.
Yeah. So the way that attention is typically calculated, the complexity grows quadratically with the length of the input sequence.
Uh-huh.
So you can imagine if you have a really long sequence, like a paragraph of text or a long video clip, it just becomes incredibly computationally burdensome.
Okay, yeah. It's starting to feel overwhelming.
Yeah.
I can see why researchers are trying to figure out how to make these things more efficient.
Right.
Yeah.
Well, that's where the reformer comes in. The reformer really tries to tackle these challenges head on. And it uses three key techniques:
Okay.
reversible layers, chunking, and locality-sensitive hashing, or LSH attention.
Okay. Let's go through them one at a time because some of those sound a little intimidating. Let's start with reversible layers.
Okay, so imagine you're building a tower of blocks, right? And to reach a higher block, you need to remember the exact path you took from the bottom. With normal layers, that's essentially what the model has to do during backpropagation. It needs to store all of those activations from every layer.
So that's where the memory problem comes in, storing every single step.
Exactly.
Okay.
Reversible layers are kind of like having a magical elevator in your block tower. You can just go up and down freely without having to remember every single step.
That sounds a lot more efficient.
Right.
But how does this apply to the model?
So essentially, with reversible layers, you can reconstruct the activations during backpropagation without needing to store them for every layer. So instead of remembering every step, you just need to know the current state and how to reverse the operations.
Okay. That's really clever. So you just ditch all the extra memory you need to store every single calculation. That must make a huge difference.
It really does. So this removes what's called the n times factor from memory usage, where n is the number of layers in the model.
Okay.
And the best part is it doesn't actually compromise the model's performance.
That's amazing. Okay, but that's just one. The reformer also tackles, the massive calculations within those feed-forward layers with something called chunking, right?
Right. So instead of building one giant unwieldy tower, imagine breaking it down into smaller, more manageable sections.
Okay.
So that's essentially what chunking does.
Like dividing a big task into smaller subtasks.
Exactly.
But does that actually save on computing power?
It does, because instead of processing the entire activation within the feed-forward layer all at once, chunking breaks it down into smaller pieces, so it reduces the memory needed at any given time. So it's like you're still doing the same amount of work, but you're just organizing it differently.
Oh, I see. So reversible layers tackle, the memory burden across the layers, and then chunking kind of breaks down the massive calculations within a single layer.
You got it.
Okay,
Oh.
got it. Now let's talk about the most intimidating sounding thing, LSH attention.
Okay, so it sounds complicated, but the concept is actually quite elegant. Imagine you're searching for a specific book in a gigantic library, right?
Yeah.
LSH attention is kind of like having a super efficient cataloging system that quickly narrows your search down to a few likely shelves instead of having to search every single shelf in the library.
Okay, so like quickly finding the most important information without having to look at everything.
Yeah.
But how does this work with like AI and attention mechanisms?
Right. So in a traditional transformer, the attention mechanism calculates the relationships between every single word or element in the input sequence.
Yeah.
And this involves a ton of calculation, especially for long sequences.
Yeah.
So LSH attention speeds things up by using a technique called hashing.
Okay, hashing, what is that?
Think of it like assigning each book in the library a unique code based on its genre, author, and keywords. Then, when you're looking for a specific book, you can quickly find all the books with similar codes, which will likely be located on the same shelf or in the same section.
Okay.
So LSH attention uses a similar principle. It groups together words or elements that are likely to be related.
Okay.
And this drastically reduces the number of calculations needed.
Well, that's neat. But I mean, there's got to be a trade-off, right?
Right.
Like, what's the downside of using LSH attention?
So, yeah. It is an approximation. It doesn't, capture every single detail of the relationships between words or elements.
Okay.
But the good news is that its accuracy improves as you use more Haring rounds.
Oh, okay. So it's like a balancing act between, speed and accuracy.
Yeah.
But does the research show that this approximation actually works?
Yeah, that's the exciting part. The research shows that LSH attention can actually achieve performance that's really close to the original full attention mechanism.
Wow. Okay. That's impressive. So these three things, reversible layers, chunking, LSH attention, all kind of work together to make the reformer much more efficient.
Exactly.
Got it.
And this has huge implications. We're talking about making AI more accessible to researchers and developers who, might not have access to massive server farms, who have limited resources.
Right. That is a game changer.
Right.
But okay, we've been talking a lot about efficiency.
Yeah.
What about the actual results?
Right.
Like, what can this thing actually do?
Yeah, that's a great question.
Let's talk about some of the experiments and see how it actually performs in the real world.
All right. So before the break, we were talking about how, with the reformer being so efficient, it could open doors to new applications, right? Not just make existing stuff faster.
Right. Yeah. And I really want to hear about that. What kind of applications are we talking about? Where could this thing really shine?
Okay, well, one area that I think is really interesting is music generation. Imagine training an AI on the complete works of musical giants like Bach, Beethoven, Mozart, not just snippets. Every single note, every nuance.
Wow. Yeah, that would be an insane amount of data. Could the reformer handle that?
That's where the reformer's ability to, process those really, really long sequences comes into play. It could analyze and learn from these massive musical data sets, and it could generate music with a depth and complexity that we've never heard before.
So we're not just talking about, creating simple melodies. This is like AI composing symphonies.
Yeah. Exactly, exactly. The reformer could like analyze different musical eras and genres, right? And it could learn to blend those influences in completely new ways. I mean, imagine like what this could do for film scores or video game soundtracks or even like personalized music experiences tailored to like your specific tastes.
Yeah, I can just imagine the soundtrack to my next epic adventure. Okay, music generation definitely sounds promising. What other fields could this efficiency boost help with?
Another area is video processing. Right now, if you wanted to use AI to like analyze a long video, like say, an entire movie, it would be so resource intensive.
Yeah.
The reformer could change all that.
So instead of just analyzing like individual scenes, we could use AI to understand like the entire narrative arc of a film.
Exactly.
Wow, what kind of insights could that unlock?
Well, I mean, it could change how we tell stories, right? I mean, we could use AI to analyze plot structure,
Hmm.
identify subtle emotional shifts, and maybe even predict how audiences will react to different scenes.
This is starting to sound like something out of Minority Report or something,
Yeah.
like AI predicting human behavior. But beyond just entertainment, what about applications in like scientific research? I mean, there's got to be a lot of potential there too.
Absolutely. So think about genomics. Analyzing an entire genome involves a massive amount of data.
Right, because genomes are like really long and complex instruction manuals.
Yeah, exactly. And so, with the reformer's ability to process these long sequences efficiently, we could analyze entire genomes much faster and for way less money.
That could lead to some pretty incredible breakthroughs in personalized medicine.
Right, because then you could tailor treatments to an individual's specific genetic makeup.
Exactly.
And it goes even beyond personalized medicine. I mean, imagine using the reformer to study the evolution of, different species or track the spread of diseases or even design new drugs based on, like a really deep understanding of genetic interactions.
Wow. Yeah, the potential for healthcare and scientific research is huge. I mean, it really sounds like the reformer could be a total game changer. But we've talked a lot about the exciting possibilities. I'm curious about like your thoughts um, on the potential downsides.
That's a really important question. Because as with any powerful technology, we need to be really mindful of the risks. If the reformer paves the way for even more powerful AI systems, it brings up a lot of questions about how we control those systems and make sure that they're used responsibly.
So it's not just about pushing the boundaries of what's possible. It's also thinking about the consequences.
Exactly, exactly. As we develop increasingly powerful AI tools, it's so crucial that we have open and honest conversations about the ethical implications, the potential for bias, and the need for transparency and accountability. We want to make sure that AI benefits everyone, not just a select few.
It sounds like we need to be as innovative in our approach to responsible AI development as we are with the technology itself.
I completely agree. I mean, the reformer's focus on efficiency could actually be a catalyst for, a more sustainable and equitable approach to AI development. So it's not just about doing more with less, but doing better with less.
I like that a lot. So for our listener, what's the one key takeaway here? What should they be thinking about as they learn more about AI and how it's changing so rapidly?
I think the most important takeaway is that, AI is an incredibly dynamic field. What seems like science fiction today could be reality tomorrow. So stay curious, keep learning, and be prepared for some really incredible advancements in the years to come.
That's a great message. So let's move on to the final part of our deep dive and explore some of those bigger questions. So we've talked about the technical side of the reformer, right? Like
Right.
all the nuts and bolts, and we've talked about some um, really cool potential applications,
Yeah.
and even touched on uh, the need for responsible AI development.
Right.
But now I kind of want to step back and think about the bigger picture here.
Yeah, I like that.
Yeah.
I think it's important, it's not enough to just understand the how.
Yeah.
We need to grapple with the why.
The why, exactly.
Like, what does the reformer tell us about where AI is going?
Exactly. This feels like, it's not just some like cool new trick.
Right.
Like this has the potential to, really change how we think about AI and what it can do.
Totally. Because, for a long time, the narrative when it came to like powerful AI, it was all about vast resources, right? Supercomputers,
Mm.
massive data sets, tons of money. The reformer kind of challenges that assumption.
Yeah, it's like it's democratizing access to powerful AI,
Right.
making it possible for smaller research teams, startups. Heck, maybe even individuals could work on this stuff.
Totally.
What kind of impact could that have on the field, do you think?
I mean, I think we could see this, this explosion of innovation, right? Like all this creativity,
Yeah.
as those barriers to entry just like crumble, When the bottleneck is no longer computational power, it's human ingenuity. Who knows what people will come up with?
It's like it's like giving a paintbrush to someone who's only ever seen the world in black and white,
Oh, that's good. Yeah.
and then suddenly they've got like this whole spectrum of color.
Exactly. And then, instead of relying on these few monolithic AI models, we could see this whole like diverse ecosystem emerge.
Oh, wow.
All these specialized AI tools, each one like excelling in its own niche.
This is getting me really excited. But let's zoom out even further.
Okay.
If we're talking about democratizing access to powerful AI, what does that mean for like society?
That's the big question, right? Like, I mean, as AI becomes more efficient, more common, more deeply integrated into our lives, like, how's that going to change things? How will it impact how we work,
Yeah.
how we learn, how we interact with each other, how we even understand our place in the world?
It feels like we're at a turning point.
Yeah,
AI could be this incredible force for good,
yeah.
but it could also lead to, some unexpected consequences. We got to be careful.
Oh, absolutely. I mean, that's why it's so important to think about ethical development, right? Really
Mhm.
consider the potential impacts of these powerful technologies. I mean, we need to make sure that that AI is used to, empower people, not control them.
Right. Yeah. It's a good reminder that technology isn't inherently good or bad.
Right.
It's all about how we choose to use it.
I totally agree, and I think the reformer, with its focus on efficiency, it could actually be like this, this catalyst for a more sustainable and equitable, approach to AI development. It's a shift in perspective. Bigger isn't always better.
Right. It's not just about doing more with less. It's about doing better with less.
Exactly.
I love that. So as we wrap up our deep dive today, what's the one thing you want our listener to really think about?
I think, if the reformer teaches us anything, it's that a lot of the limitations that we see in AI, maybe they're more about, our own assumptions than the technology itself. What might have seemed impossible yesterday, could be within reach tomorrow. So never stop questioning, never stop exploring, and never stop pushing the boundaries of what you think is possible. The future of AI is, in a lot of ways, still being written, and we all have a role to play in shaping it.
That's a great message. The future of AI is not set in stone.
Right.
It's something that we're all creating together.
Yeah.
And that is the essence of the deep dive. So until next time, stay curious.